it's not as clear cut maybe as you think, but anyway, that's a discussion for another time. I had a coworker, and I've gotten
better over the years because my fiance won't ride won't ride in my passenger seat.
So men take more risks, but, and this is general blanket statement, generally.
Now that's your recording, man.
I am recording, so I have to be extra careful here, but generally have better motor, like
hand-eye coordination.
yes, and you know, who knows how that sort of balances, the two balance each other out. I had a colleague who now this and I have to be careful here, but she's of Asian descent, and she would make fun of Asian drivers all the time, but especially female Asian drivers. Anyway, you know, and it's kind of, I'm curious how stereotypes like that get started, and you know, who knows if they're actually true. I mean, I'm sure we can all think of a time where any sort of demographic did something stupid on the road, but anyway, all right. So Brittany, I'm going to pick on you a little bit before we get into the rest of today. What does a normal distribution look like? Okay, I was going to say, you can't say that, but just describe it.
So a bell curve?
Yes, you could just say bell curve.
Oh, okay.
So on the bell curve, where would you, if you had to draw where the average was, the mean or mu, where would you draw it?
Very top.
Good. Yep. Yeah, where it's the tallest, right? The curve is the tallest. So one thing we're going to talk about is density. So density really is just the height at any point on the curve. Just remember that if we talk about density, it's the height at a certain point. And Z is a measure of dispersion, just like the standard deviation is. So it just tells us how spread out that curve. If it's a really narrow and tall curve, or if it's really flat and spread out, that's basically what those numbers tell us. We had reviewed this before. Now to get into our new content for today with the quantitative analysis in signal detection theory. So P open parenthesis, S in quotation, bar, S close parenthesis. It's statistics does have its own sort of language, right? I mean, you kind of have to learn the language while you're learning the theory at the same time. So what all this means, for example, with this hit rate, is the probability of detecting a signal or responding that there's signal when there actually is signal. So that's our hit. And so when we look at these two probabilities together, that creates a hit rate. So it's a ratio of the two. You would want that to be 1, right? 1.0. But obviously it's usually not. So given that the probability of detecting a signal, given that there is a signal, how would you translate this one into English? This one right here. So this in the same way, but
detecting a signal that's not there.
So that's this one. The probability of detecting a signal when there's just noise.
The inability to detect.
Well, that's
Okay.
same in this rate. So it's saying reality there's a signal, but your response is there's no signal.
Yes, maybe I crossed what you said. I don't know. Yeah, so this one is the probability that you detect noise, you think there's noise, when there's actually a signal. The probability that you detect a signal when it's actually just noise. and the probability that you detect noise and it is actually noise. So these terms are important for us to remember. We use some different terminology the other day. We called hit rate, well, we called it a hit, but it would also be a true positive. So going with the true and false, positive and negative, what would this be then? If this is a true positive, what is this? Yes. So miss rate is the same thing as a false negative. I just want to double check and make sure that this is recording. It's not so bad in this class, but when I mess it up in 603, that's 3 hours of lecture that I have to like redo. Anyway. Yes. So Brittany, why don't you do the next one? Okay. It's only going to be a 50-50 shot. Okay. Because we know this is a true positive, false positive. So these are both going to be negative. Just one is true and one is false.
Okay,
So let's do this one. So it's either a true or a false negative. You got a 50-50 shot.
the true negative.
So this one is true negative. And this one is false negative. So here it is a negative, or it is noise, and we thought it was noise, so we were right. Here it was noise, but we thought there was a signal. So we got a false. Sorry.
Was there
I'm messing this up. So this is a false positive.
So I was right.
I misled you. This is a false positive. Man, I only got 3 hours of sleep last night, so forgive me when I start messing stuff up. Feel free to correct me if you're like, that's wrong, Dr. Reed. Okay, so this is false positive. This would be a true negative, right? And this would be a false negative. So here's our little table, and it's just a way to sort of visualize the same thing. And we could we might as well draw one. I like to draw. You guys know that. Maybe I like to draw too much. Oh, yeah. It's not that big a deal, so I'm just going to draw it on the board. So if our response up here is that there's noise or signal, and over here the reality is that we have noise or signal, which I want to put these terms, hit rate, miss rate, in here. So which one goes where? Amber. So where would hit rate go? It's good to start with the easy ones, right? Or, ones that are a little more straightforward, and then you can kind of eliminate option.
Top left corner?
So top left, in reality, there's no.
No, it'd be the bottom right.
Yes.
They both hit.
So this would be hit rate. Amy, where would false alarm rate be?
Right above hit rate.
Yes. So we thought there was a signal, but there actually wasn't. Sorry, I'm double checking myself because like I said, my brain is not on, it's like on 3 cylinders today. Brittany, where would miss rate be? So we thought it was noise, but it was actually
Sound. So
an alarm.
the bottom left.
Yes. So that only leaves our correct rejection rate for there. Okay, so this is why knowing about distributions was important. If you were to plot the noise versus signal on, or well, actually, the responses for noise versus signal, you could get two distributions that look kind of like this. So you've got a noise bell curve and a signal bell curve. One thing, if you ever hear the term signal detection theory schematic, this is what it's referring to, is plotting the two curves next to each other. And you would hope, now, so you see that all of this area under the red is a hit. And all this area, well, I mean, besides, where the blue comes in. So above the blue, but below the red represents a hit. Below the blue and above the red is a correct reject. So you want to maximize how much is under those parts, right? And you want to minimize how much is down here. So if we were moving these two curves, how could we move them to minimize the area under here, the overlap? Yes, good. So we can move them apart. So if we were plotting our noise versus signal, we would hope that our curves wouldn't overlap at all, that they'd be as far apart as possible. But generally, the world is imperfect, and there is some overlap. So we will have some false alarms, and we will have misses. And I say that especially when humans are involved, then you'll have this. Sometimes machines can get it all right, but anyway. So there's I guess it's not here yet, but I mean, not on this graph. Are we good with this one? Okay, there's a term called decision criterion, and that is represented by the X sub C. And that, the way we find that is we take the average. Well, let me back up. So we look at the mean for the signal, the mean for the noise, and then we take the average of the distance between the two. So, if this was if we were plotting this, and let's say it was 10, if we took US minus UN, and then average that amount, then we would get, that's how we would find our decision criteria. Does that make sense? The decision criteria it's basically, it's in the middle of the two means. That's how we find it. But you'll notice it doesn't line up necessarily. And I don't know if that's just because this isn't to scale or on purpose, but generally it's not always, I mean, often it's not in this intersect where the two lines come together. And we'll talk about that in a minute. Well, this can apply to multiple fields. I think that's it for this one. And Z is its own unit, interestingly, here. It's in Z units. Sensitivity is represented by D prime, although sometimes it's represented by P, not to confuse anyone. And so I'm not totally sure what P Dr. Fogelman is referring to in one or two slides here, but it could be sensitivity. It could be the probability, simply the probability. And I think it's likely the probability. So D prime is the difference between these two terms. So the noise minus the signal in Z units. in epidemiology, there's another, again, not to get too confusing, but sensitivity is used in epidemiology when evaluating screening tests. So like I was talking about my son's friend who, we hope doesn't have cancer. There are multiple measures of a test's accuracy, and sensitivity is one of them. So it's used in epidemiology, and it's estimated using just using the numbers in these boxes, actually, and not in this way. And then there's response criterion. So what is a ratio? If we took a ratio of the gun owners versus non-gun owners in Yavapai County.
Be like a percentage.
Okay, so it's like a percentage.
It's kind of a competitive.
Okay, so we are comparing things. But let's say if we were to calculate the ratio of gun, I've never lived somewhere where guns were so important as in Yavapai County. I just didn't realize it. I like to go shooting, but I didn't realize it was that big of a deal. So let's say that there are, I'm going to make up some numbers, but let's say there are, and these are way low, but let's say I'm gonna do a little bit of a comparison here to like New York City and then Yavapai County, and let's say in New York City total there are 500 gun owners. I know this is not accurate, and then there are there are probably like 10 million people. And then in Yavapai County, there are 500 gun owners, and there's 1,000 people. I know those numbers are not accurate, but
That is as accurate as you can get.
maybe it's not too far off.
I think that New York has more gun owners.
It does. I'm just
Not registered.
You said that, not me.
You know what I was sleeping.
So
Very angry up there.
So what number would we get if these were accurate and we did the math? So we could take 500 and just move the decimal over 7 places, right? So let's see, 1, 2, 3, 4, 5, 6, 7. So we've got 4 zeros, 0.00005. And here we got 0.5. So this is a ratio of the gun owners to non-gun owners in Yavapai County. Although, well, I'm saying a ratio, so it's not that 50% own firearms. So yeah, this should have been higher. There are probably more gun owners to non-gun owners in Yavapai County, and so we probably should have said something like that. Let's do that. So there are 1.5 gun owners. So if there were 1,500 gun owners and 1,000 people who didn't own a firearm, then there would be 1.5 people with a gun for every 1 person without. So that is a ratio. And in New York,
Very small.
right, for every 1, 2, 3, 4, 5, 10 to the 5. For every 10,000 people without a gun, there's 1 person with a gun, if these were true. But that is what a ratio is. Are there any units to a ratio?
And you're saying gun owners, that's technically a unit.
So that would be a unit. when we interpret it, that we attach that onto it, but by itself there are no units associated with it. It's just a number, and that's one of the few times where we have something that's just a number. So what? So back to response criterion. What we're doing is we're looking at the height. So where that decision criterion crosses these two curves, we're looking at the height to each of those intersections. So we look at the height from the signal, the Y signal, and then the Y noise, and we take a ratio. So I mean, I'm going to make up some numbers, but let's say this is, you have an example now. So let's say this is 8 and that's 10. Looking at this, what would our ratio be if the signal is 8 and the noise is 10 to that intersection point? No, so think of it as an equation. So we're taking the ratio of at the decision criterion, we're taking the ratio of signal to noise. Instead of gun owners to non-gun owners, it's the signal to noise. So here, this would be signal and this would be noise. So we'd have signal to noise. So for every 8 signal, there's 10 noise. And we'll talk about what that means exactly in just a minute. So, and this is the P that I'm not totally sure if he's referring to sensitivity or probability. I think it's probability though. But Z and P are related to the dispersion. And to estimate Z, you can either do this equation or you can look at a PZY table. And I need to post the assignment for this this topic, but I will give you an Excel table that has both the table or the calculator, so you don't have to think about this too much. But and we're actually going to use it as long as we have time. I need to end a little bit early, but anyway, so you can either use the table and look it up or use this equation. And you kind of have to do it in this order because Z is included in the equation for Y, which is the density. So Y is the density. When I say density, I just mean how high is it from the floor to whatever point we're talking about. It could be here, it could be here. So what is that height? What is the value of Y, basically? That's all that means. So we have to find Z first before we can find Y. And then the response criterion, we can either use the two Y's or you can use this equation. So beta represents the response criterion. So here's the interpretation for beta. And I want to apply this to the example we had just a minute ago. But if beta equals 1, that means there's no yes or no bias. If beta is less than 1, then there's a yes biased response. And if it's greater than 1, then there's a no biased response. So remember that, and I'm going to go back. Beta less than 1 is yes, greater than 1 is no. So let's use an example. Let's say that, well, has anyone had an experience where you had an alarm or, you know, something that was, I'm thinking of an alarm, but you ignored it, and then later you realized you shouldn't have ignored it, or the reverse. You responded, and then you were like, why did I do this? This was a waste of time. Any examples?
Brownies.
Okay, so what happened?
Like that a little crazy.
Okay, so what was the signal? Was there a smoke alarm or
No, I really don't remember. I know I set a timer and I'm like, oh, I'll get it in another 5 minutes. 10, 15 minutes go by. I'm like, oh crap. It just came to me and I'm like, oh, that's
I've done worse. I actually this is why I was single. I was baking some brownies and I forgot about them, and like I lived in an apartment with so there were 6 of us together. I mean, it was 3-bedroom apartment. Yeah, it was it was a good deal. So was trying to save money, but yeah, two bathrooms split with 6 guys. Yeah. Anyway, but anyway, we for some reason like we all left. We went to do something.
You left the brownies in the
I
oven.
left the brownies in the oven. So when we got back, there was like this haze throughout the whole apartment, and the brownies were devoid of moisture. I mean, I don't know how to. I called them charkies instead of brownies because they're like charcoal. Like
So
anyway.
I just got finished baking something in the oven and I forgot to turn the oven off. So I went to bed.
Oh, so you've done it too.
No, nothing was burnt in there. I just
Oh,
left the oven on.
okay.
There's no way to tell unless you look.
Yeah.
I didn't look until the next morning. I don't think so.
So was it just really hot in it, or
It
I mean
was extremely hot in that apartment. Extremely.
okay, well,
Conditioning kept on coming on really quick.
so I guess I've done the worst, but anyway. Okay, so let's say so the timer that you set was the signal, and after that experience, I'll bet you learned a little bit of maybe yes bias. Right, where I mean, I don't know if the example fits exactly, but it's close enough. So if we were to plot that, then what we might see is, I'm gonna erase that if I can find.
On top of the little SBN thing.
Oh, is there? Oh, over that one. I never look over there. But yeah, no, yeah, I know. That would have done as well. So I want to plot what that might look like. Let's do colors. It won't be exactly the same because I don't have blue, but we'll do green and red. Yeah, not exact, but
Close enough.
yeah.
Close enough for government.
Yeah. So we'll have 2. Let's say, I mean, we have 2 different decision criteria. Say that's 1 and that's 2. So remember, this one is this is noise, and this is signal. Yeah, I know he usually brings them, right? Dr.
Yeah,
Fogelman,
well,
I'm sorry.
I always make some brownies for you. I never got brownies. Really?
Really?
Oh yeah, so she felt misery for the master students going through these exams. So she used to only make them for the master students. And then she started doing it for the undergrad.
Well, she gypped us.
Yeah. Oh,
I'm upset.
delicious, moist, awesome brownies. I look forward to exam day every time.
Well, that's why she did it.
Yeah, I have not met his wife. I need to meet his wife.
I've never met his wife either, but I love her brownies.
Did you please give her a thank you note?
Oh yeah.
Oh, very good. I was gonna say if you didn't, maybe that's why she stopped giving us brownies.
Wow.
Oh, y'all's fault. She hated teaching undergrad though.
Oh, I didn't know that.
I went in and I'm like, should I take this class? It's like, I don't like teaching undergrad.
Oh.
No wonder they switched them to full time.
Yeah.
I like it more.
Well, and that's why I picked up these two classes. So he's all graduate. Yeah, I mean,
Brilliant. Yeah.
graduate students are a little bit easier in some ways, but
Unless
anyway.
you're ready.
Oh, well, okay, yeah, in general, but there are always those, people on the fringes. Like you guys, if this was the undergrad curve and this was the grad curve, you guys are up here. Okay. And there are some grads that are down here in easiness, but I mean, for the professor. So anyway, so here would be our Y noise and our Y noise right there. And here would be our Y signal and our Y signal right there for the different scenarios, 1 and 2. But let's contrast maybe your pre-burnt brownies to post-burnt brownies self. Okay. So let me remember, it's the signal to the noise. That's the ratio, is signal to noise. And when we're less than 1, it's a yes bias. When we're greater than 1, it's a no bias. So pre-burnt brownies, Brittany. Let's think about this. So we're comparing these two here. This one is running out, 1 and 2. First, let's think about it in terms of the ratio. So if we were to take ratios of the signal to noise for each of these two, so this is 1, each of these lines. Maybe I should just draw a line here.
So is one of these lines burnt brownies and another one's not the burnt brownies?
Yes.
Okay.
So if we take a ratio of the signal to noise here, are we going to be more than 1 or less than 1? Okay. So here, because the signal is going to be really little, and we're going to have big noise. I mean, it's just the height, right?
Oh, okay.
Okay. So we look at that ratio of the two, and we see, okay, yeah, we are less than 1. So beta is less than 1. And if we look at this side, is beta, what is beta? Greater than 1. So that's in terms of beta. Now let's just think about it conceptually. In which one was there signal, but you suppressed it, or, pretend that you interpreted it as noise? I mean, the first one, right? So which of these two lines, I'm trying to highlight these lines, and it's not really.
What is the one on the right then? Or this?
It would be on the left, wouldn't it? Because you get the signal, but you ignore the noise.
So with which line were you, which line tends to emphasize the noise over signal?
I don't remember it.
No, one. It's closer to the noise.
So you were both right at different times, but so one emphasizes the noise over signal because it's so big. So you've moved. This is the pre-burnt brownies, Brittany. Okay. You heard the alarm, and you're like, you kind of dismissed it. I mean, it wasn't technically noise, but we're gonna say, I mean, you detected the signal, but your response was,
I'll get it later.
yeah, it's kind of like noise, as if it had been noise. So pre-burnt brownie, Brittany would be right here, but then after, I one-upped her, so. But after that experience, then maybe with some of the decision criteria that you use in deciding when to pull the brownies out of the oven, your decision criterion moved up to here, so that now you overemphasize the signal. You emphasize signal over noise, so that if you think the alarm went off, you'd be more likely to get up, even if maybe it actually hadn't. It was just, I don't know, some other noise that kind of sounded like it. You would get up and go check it out. All right, so this is an example of no bias. This is an example of yes. So let me write that here. And okay. So this is an interpretation of the signs for Z for the noise and Z for signal. Let's back up a little bit. Remember, Z for noise and Z for signal is just the distance from the mean for noise to where the middle is, the decision criterion. And Z for signal is the same thing, just on the opposite side, the mean for the signal. So that's what those are referring to, is how far is the mean for signal from the decision criterion. So we talked a little bit about this before, except without the Z part. Would you want these to be big or little? You want them to be big, because if they're big, that means that they're spread out. And generally, we want those to be big. I don't know, maybe there are times where you want false alarms and misses, but I'm not sure when when you want that. Generally, yes, yeah. Generally, you would want to minimize the misses and at the expense of having some false alarms.
You don't have too many wolf cries.
Yeah.
And then people become desensitized.
Right. And that's like in emergency management, it's a fine line you have to balance. So like we had the active shooter drill, or whatever it was called, the lockdown drill. So one, everyone hates drills, even if there are a few exceptions for people who like really don't want to be in class, but they go anyway, or I don't know, they're unprepared for an exam and the drill goes off. The kid who pulls the fire alarm because in high school anyway. So generally people don't like drills, but also if you drilled too often, so you want to drill enough that people know what to do in the real thing, but you don't want to drill so often that people, like you said, it's like crying wolf, and people are like, another fire alarm, just like, the car alarm, another fire alarm. So they just keep going. And then actually, yeah, there was a fire. And
Yeah, where we have to do red caps on the lifeguard.
Mm.
I manage all the other lifeguards. Like we have to red cap them and they're doing like drownings and stuff. Another one. Another one.
so wait, so while you're on duty, like they have someone pretend to
Drown.
really,
Or cut their arm off. Or say, heart attack.
how do they fake that? The
Very carefully.
cut the
I go there and I
Cut
lay
arm
down
off.
on the floor and I start having a seizure.
Oh.
I start screaming. My arms, we have fake blood too, but I want to be real mean.
Oh wow.
Just make sure you don't give any children heart attacks.
Is this why people are there? Yeah.
Wow.
It's like a lifeguard's like guarding the pool and nobody's there. I'll go do it to them. Like it's actually people who I want. Make them come. Oh my goodness.
Why has everyone seen Sandlot?
Yes.
Sandlot?
Yes.
You who has seen it? Sorry, it was a bit of a tangent, but you have not, Amy?
No.
You need to watch it.
When it comes to movies.
Dude, you're my
So-
age.
You need to see Sandlot.
The most ridiculous movies I haven't seen, like Star Wars. That was 19 when I finally seen Star Wars. It was a Star Trek. My parents were Star Treks, and it was all that was allowed in my house.
You need to watch The Sandlot.
Sandlot.
But
I will text you.
You can. My fiance will be all over it.
there was
I yelled at for not seeing V for Vendetta. Oh, I
Finally saw it last year.
didn't want to see it.
So real quick, the decision criterion could be, as we showed, in between the two. So the mean for signal is further to the right, and the mean for noise is to the left. And so the decision criterion would be in between. So that's what this is. And if you look at the Z for each of those, the Z for noise is going to be positive. This is good enough. Positive because we did the criterion minus, or where am I trying to get here? Well, if we subtracted the Z scores from the decision criterion, sorry. If you subtract this from that, it'll be a positive number. But if you subtract this, the mean for the signal curve from the decision criterion, it would be negative. Does that make sense? So XC minus mu n, let's say this is 10 and that's 5, 10 minus 5. So let's say this is 15 for the signal mean. We would do 10 minus 15, so we're going to get a negative number. So that's all that's saying. If the decision criterion is less than the noise mean, then it will also be negative. And if it's greater than the signal mean, then they'll both be positive. So it's just changing where it is. It's going to change the sign for Z. All right, so let's do an example, and then we'll be done for today. So we're going to talk about TSA. I'm assuming this is TSA. Oh no, man! It's you're recalling memories you've tried to suppress. Maybe, I don't know.
You see Adam Ruins Everything?
No.
There's an episode on TSA, and it makes me hate TSA that much more.
They're easy to
They're
pick
not
on,
there
but
for a reason. They're there for a reason, but it's not the reason.
okay. That's something I'll have to watch.
You like it. It's a really fun show.
Huh?
They give
Adam
citations.
Ruins Everything.
It's on Netflix right now.
Okay.
They give citations throughout the whole thing, so you can go onto their website and read the articles for yourself.
Oh, really?
And it's great. He really does do a quality done job of telling you things that you don't realize are there.
Interesting. Speaking of signal detection, when like the gorilla with the basketball passes. So the goal is to detect contraband items. So what do you think the signal is?
Contraband.
So when there's contraband, that's signal. Hopefully pick up on it. And so what are all the other suitcases and stuff? All the normal bystanders. Yeah, so that's the noise. So all the regular stuff is noise. And so the little grannies and everyone else who's normal who goes through, not going to find anything in there. But they plant 20 signal suitcases that have contraband. And so the goal is to correctly identify the contraband. And if you do, that's a hit. Let me, we're going to go to Excel. So I want to transfer this to the board.
Well, that's why they can't catch anything. I want to clear with the knife when I'm realizing it. Came back 2 hours later to catch a different plane, and they did finally catch it. And I was in there.
Oh.
I'm like, really? And I was like, yeah, I walked through this morning with it in my purse. And they're like, please don't tell that to my secret.
So did you lose your knife?
Yeah.
Oh.
Well, that's why I buy them on sale and bulk.
There you go.
$75 knife for $40. Seriously? Yeah, they buy. They buy whenever they do a massive sale.
Black Friday or Cyber Monday. That's Christmas.
Yeah. It's amazing.
All right, so we have
And they're really quality knives.
response. Maybe I should have done that different, but speaking of human factors, let's do it different. Color coding the category. All right, so now I don't have something to contrast. I'll try this blue. Speaking of human factors. Okay. All right. So we drew these before in the boxes, but if there is noise, it's just the regular luggage, and we're like, oh yeah, that's just regular luggage. Then what is that called? Correct rejection or correct rejection rate. What about when there is contraband and we're like, oh, that's just regular. It's the little granny's suitcase. It's not going to have anything, but it does. Huh? Yes.
When you try to go through security with sharks and things like that, they don't like that.
So what was this? Huh?
How is it MR and not a FAR?
So a false alarm means you thought it was signal, but it was nothing.
Yeah.
Like someone pulls the fire alarm and everyone runs out of the building, but there was no fire. So there was no contraband, or no. That's a false alarm. Yeah, sorry. Yeah. So there was no contraband, but there was a signal. There was an alarm.
You get stopped anyways because there's just a bunch of sharks' teeth.
So which way do you read it from then? From the top going to the left?
Either way. So the way if you want, think of, just pick one side to use all the time. Let's use the reality side. So there is contraband. Do we figure that out or not? If we do figure out that there's contraband, and there is, then that's what do we call it? a hit. So that's the hit rate. And that's not working very well. But if there is contraband and we miss it, it's a miss. So there's contraband, but we missed it. So it's called a miss. Yeah, they missed Amy's knife. And they missed the granny with cocaine or something. So then let's say there is no contraband, but the little, I don't know, the machine that scans, like it alarms and the swarm of agents descend upon you and your bag. What is that called? A false alarm. Right. And it's really, it's done. Yeah. That's pretty good. All right. So I just wanted to review that real quick. And now I'm going to erase these. And we're going to put numbers in. So it shows some of the math there. Let's put these numbers in. So correct rejections, 70. False alarms, we had 10. Oh boy, 10 out of 100. We had 4 misses. This department is not doing. They're not doing very good. These are probably unrealistic. I mean, I hope the real TSA is not like this. It's like
I've gotten more false alarms than I have ever dealt with in my life in the last 2 years.
Wow.
I have been stopped probably 80% of the time I've gone through. Because there was something funny in my bag, and it was my headphones. It was my car keys. It was shark's teeth. It was some of the most.
Why did you have shark's teeth in your purse?
I've never seen a shark's tooth in my life, so I picked up like hundreds of
Don't put it in your purse.
Yes, that's how you get it home.
All right, so so maybe these are more realistic than I'm thinking. I don't know. I hope not. I hope they do better than that. But a rate it's the same idea basically as a ratio. So we talked about a ratio before. You're comparing one number to the other. Like for every, so there are 15. Let's say there are 1,500 gun owners in Yavapai County and 1,000 non-gun owners. We created a ratio that was 1.5. So we're doing the same thing here, although none of these should be over 1. We could get 1 if they had 100 hits and 0 for everything else, then their hit rate would be 100%. Like that's awesome. But anyway, so let's look at this. So we need to create the ratio for each of these. And let's draw another box where we have the rates. All right, so for correct rejections, we got 70, but how many incorrect rejections did we have? You could think of it that way. How many times did we reject or how to word this? Okay, so basically what we want to know is, of all the times where it was just the noise, how many times did we actually say, yeah, it was noise? Okay, so that's one way to think of it. So what would we do? What could we do in terms of these numbers to figure that out? Of all the times that it was just noise, what is our rate for getting that right? We had 70 correct rejections. Not quite.
Over 80.
70 over 80. So 80 times. So they said they planted 20 suitcases, that had stuff out of 100. So there are 80 suitcases that had nothing. And of those 80 suitcases, we got 70 of them. This is probably, I think this is their best number. The others are much worse. But so they did okay at distinguishing the noise.
Any time they successfully did stop someone from
So yeah. So oh
I made a joke to one of the TSA.
oh no. Yeah, that's
Randomly selected going through College Station, and I made a joke. It's because he's from South Africa. He really was from South Africa. After he got randomly selected, they got his luggage all the way through. They had to stop and check for drugs because there was a drug alert that went off on his back.
oh
For like 6 months after.
I remember I got an alarm for no reason, just randomly selected. I was like 15 and they had to pat me down like crazy. I'm like, what the hell?
Pat down, it was not fun.
Yeah.
They were touching places they had no right to touch.
Huh.
I'll tell you though.
I was 15. I'm like, why?
Oh, try having a medical equipment coming out of you. That's really awkward.
And we got off topic.
Okay. So let's look at false alarm rate. So of all of the noise, how many times did we say, did we have an alarm when there really wasn't? So it's 10 times, right, out of 80. So that would be, 10 divided by 80 or 0.125. So notice if you were to add these up,
They equal 1.
they equal 1. So adding them up this way should equal 1. Now let's look at our miss rate. So the way to verbalize that or translate that, I guess, is how often was there signal, was there contraband, and we did not pick it up?
4 times.
4 out of
20.
20 times. So there are 20 times where there was contraband. We did not pick it up 4 times. So 4 out of 20. Oh, what was that? 0.25, 0.2. So the opposite is true, right? Of our hit, right? So how often was there contraband and we picked it up? 16 of the 20 times. So my little greenie, yeah, is not doing so well. So if you were to add up, the columns, or by column, add up the rows in a single column, does it equal 1? It does not. Okay, so that's something to keep in mind. So it's only when you add across horizontally, then you're going to get 1. All right, so for our z-score, let's use this Excel table or the calculator. So here we are finding, we're using our miss rate as that's the probability that we're going to miss contraband when there is contraband, is 0.2. It's so nice when yeah, it does it for you. All right, so we get negative 0.842, negative 0.842. So if we could also look at our our Excel spreadsheet, and we can see y is 0.28. It does it for us, thankfully. We would do the same thing for our correct rejection rate, and we calculated that to be 0.875. When we plug that in, we get 1.15, and our y is 2.06. So beta, this is math that we can do. So beta would be what? Remember, we talked about it's the ratio. Let me go back.
So it's a yes bias plus
So beta is the ratio of
one.
signal to noise.
So it's no bias.
So so we're gonna be above 1. So we just real quick, we take our y for our signal, 2.8, and we divide by our y for the noise, 0.206, and it comes out to be that number, 1.36. Because it's greater than 1, I always mix these up, so I don't want to say. Greater than 1 is no bias. And our sensitivity is 1.99. Interpreting that, that's our, now I hope I'm getting this right because I mix it up as well. I'll confirm for next time, but sensitivity is our ability to identify the true positives, basically. And then there's another term that measures your ability to identify the true negatives. And I'm gonna have to review that for something for next time, but we could do it again with different numbers. We're not gonna go through the whole process, but you would do the same thing that we did. So take these ratios. If you actually, I forget. So we're comparing the machine to humans. Okay, so this is the human performance, and then here's the machine. So who did better, the machine or the humans?
Response
It is much larger, so it appears that it had a bias towards not signaling. So you can see the ratio of misses to hits, misses to hits. It's pretty high, higher than the human. So the humans had a tendency to do more false alarms just to be safe, and the machine had a tendency to let stuff go through when it shouldn't have. So we have a lower sensitivity, lower ability to detect true positives, and response criterion 3.14. So a really high, no bias or yes bias. It is a yes bias. Dang it. No, it's a no bias. Oh. Luckily, it's a take-home exam, so you don't have to memorize that. And like I said, I got 3 hours of sleep. But anyway, so it's I have to stare at it. No bias. Okay. So the machine had greater no bias and worse sensitivity, a lower sensitivity. So humans actually did better in this situation, which is interesting. We have another, well, let's call that good. But we're comparing against another machine here. This machine did much better. You can see the miss So look at the miss to hit ratio, only 2 misses and 18 hits, and only 2 false alarms and 18 hits. So maybe they
I
tweaked,
like that machine.
yeah, maybe they tweaked the algorithm, not sure exactly what they did, but you can see the sensitivity is much higher, a lot higher than our others. So much better at detecting true positives. The response criterion was really high as well, interestingly. So that means it had a high no bias, but what that really means is the signal to no, there was a lot, it responded a lot as signal rather than as noise. All right. Thanks, guys.